This PowerPoint slideshow is on frequency distributions. Frequency distribution is just a table or graph that can display frequencies. We talked about what the word frequency means. We'll go over it one more time. The frequency of a value is the number of times that a value appears in a set of data. So if I ask 8 people to tell me how many classes they're taking this quarter, and these were their 8 answers, then the frequency of 2 would be 3 because the answer of 2 appears 3 times. It's 1, 2, 3. The frequency of the value of 3 is 2 because 2 people said 3. There's 2 3s in the data. The frequency of 4 is 2 because there's 2 4s, and the frequency of 5 is 1 because there's 1 5 in our list of data right here. And there's different ways to present frequencies. And if you have a column of nominal data in a spreadsheet, you would create a bar graph to show the frequencies. If you had a column of ordinal data, such as a column of grade levels, you would also create a bar graph. And the categories on the x-axis would follow a specific order, such as freshman, sophomore, junior, senior. If you have a column of quantitative data, you would create either a frequency distribution table or a histogram. When we talked about what the word frequency means, it's the number of times that the value appears in the data. And this describes how to create a frequency distribution table. You have the X column that lists all of the different values that were found in the column of data. And then you have the frequency column, which says how many times each of the values that appeared in the column of data. Here's another example of frequencies. Let's say we asked 10 people how many times they go to Starbucks each week, and these were their answers. Right here I'm showing you what the frequencies are. We have 4 1s, we have 2 2s, we have 3 3s, and we have 1 5. So that's why these are the different frequencies down here. Since 1 appears 4 times, 1 has a frequency of 4. Since 3 appears 3 times, then 3 has a frequency of 3, and the same thing is true for these two numbers over here. If we wanted to create a frequency distribution table for this set of data right here, it would look like this. Remember, these were the 4 answers that appeared in the list of numbers. We had 1s, 2s, 3s, and 5s. So this says 1, 2, 3, 5. And this just shows how many times each of those numbers appeared in a set of answers. And I talked about before how with some types of variables, like with age, there's too many possible values to list all of them on the x-axis. So it's better to create these groups that we see here, like 10 to 19, 20 to 29, and 30 to 39, and put those groups on the x-axis instead of every whole number. Each of those groups is called a class interval. So let's look at an example of a grouped frequency distribution table. We ask these 18 people their ages, and we get these we ask these 15 people their ages, and we get these 15 answers. This would be a grouped frequency distribution table. Each of these groups over here is called a class interval. So 20 to 29 is the first class interval, 30 to 39 is the second class interval, and this is the third class interval. So overall we have 5 class intervals in this table right here. Because 1, 2, 3, 4, 5. So each group is called a class interval, and we have 5 of them. There's also a different term called a class width. The class width is the span between the lowest and highest numbers inside each of the class intervals. So the class width is how far these two numbers are apart from each other. The class width in this example is 10 because what the class width actually is the number of numbers between this low point here and this high point right here. So let's think about how many numbers there are between 20 and 29. It might seem like there's 9 numbers between 20 and 29, but there's actually 10. We can see that right here. There's 5 numbers between 20 and 25, and then 26 to 29 gives us 5 more numbers. Well, actually, I made a mistake because there's actually 5 numbers between 20 and 24 because it's 1, 2, 3, 4, 5. And there's 5 other numbers between 25 and 29. So there's 5 numbers between 20 and there's 5 numbers between 20 and 29. I think I made a mistake. Let's see, 1, 2, 3, 22, 23, 24, 26, 27, 28, 29. There should be 10 numbers between 20 and 29. So 20, 21, 22, 23, 24. Oh, I skipped over 25. Sorry. That was my mistake. So there are 10 numbers between 20 and 29. So which is why you would say that the class width is 10. Because 1, 2, 3, 4, 5, 6, 7, 8, 9 gives you 9 numbers, and then when you include 20, that gives you a 10th number. So, and actually, if we did the same thing for each of these other intervals, we would get 10 numbers each time because there's 10 numbers between 30 and 39, 10 numbers between 40 and 49, and so on. So each of these is each of these class intervals covers 10 numbers. They all have the same width, which is why you would just say that the class width in this histogram is 10. And actually, in every histogram, each class interval always has the same class width, because you couldn't create a histogram. For example, there would be 20 to 24, and then 25 to 59, and then 60 to 99, because that would, if you did that, you would have different class widths, and you're not allowed to have different class widths. Every class interval has to have the same class width. And what if instead of doing this, what if we had a different table in which the intervals were 0 to 49. I'll do an example right here. What if it was 0 to 49, and then 50 to 99, and then 100 to 149, and then 150 to 199. In this table, we have a class width of 50 because each of these four class intervals covers 50 numbers, because there's 50 numbers between 0 and 49. There's 50 numbers in here between 50 and 99. There's also 50 numbers in here and 50 numbers in here. So we would say class width is 50. And if we had this right here, the class width would be 10. Because each interval covers 10 numbers. There's actually a formula that can give you the class width. What you have to do is you have to just choose one of the intervals. It can be any of the intervals. And then take the high number of the interval, which is called the upper boundary of the interval, and subtract it by the low number of the interval, which is called the lower boundary, and then add 1. So each of these numbers is called a lower boundary. The lower number in each of these intervals is called the lower boundary. The upper number is called the upper boundary. So every interval has a lower boundary and an upper boundary. So let's use this formula right here. Class width equals upper boundary minus lower boundary plus 1. So the upper boundary is 49. Minus the lower boundary of 0, which is right here, plus 1 at the end. So what's 49 minus 0 plus 1? 49 minus 0 is just 49. And then 49 plus 1 is 50. So we get our class width of 50. Let's do the same thing down here for the class width of 10. Here we have our lower boundary. Here we have the upper boundary. We take the upper boundary of 9, subtract it by the lower boundary of 0, and then add 1 at the end. 9 minus 0 is 9, and then 9 plus 1 is 10. So we get our class width of 10 using this formula. One thing you have to remember is that the class width and class interval are two different things. That's one thing that confuses a lot of people on a multiple choice test, is the difference between a class interval and a class width. So if you're taking an exam, it's a good idea to make sure that you remember the difference between those two concepts. This just covers some guidelines that are commonly used about how many intervals to use and what type of class width to use. It's usually better to use um, a nice number for the class width, like 5 or 10, like a multiple of 5 or a multiple of 10. So maybe 5, 10, or 20 or 50 or 100. Because if you use a class width like 7, it might look a little bit strange because then your intervals would be 10 to 16, 17 to 23. This is with a class width of 7, and then 24 to 30. It doesn't look as nice, and it's not as easy to follow or to interpret. So it's better to use multiples of 5 or 10 for class widths. Also, all of the intervals need to have the same class width. So you wouldn't be allowed to make a table like this where you have 10 to 19 as the first interval and then 20 to 49 as the next interval and then 50 to 99 as the next one. This wouldn't be allowed because the intervals have different widths, and the rule is that all intervals have to have the same class width, so this is not allowed. So we talked about histograms. In a histogram, each of the frequencies that were in that F column is shown as a bar. This is a histogram of those 15 heights that we saw on another slide. It's a histogram of this table right here. Well, we started with this data, these 15 heights. We made them into a frequency table, and then now I'm taking this table and making it into a histogram. So notice how this bar of 2 right here, this first blue bar, that's just this frequency of 2 right there, and then notice how we have 6 and then 2 next, and then 4 and then 1. So 2, 6, 2, 4, 1. Here we just have 2, 6, 2, 4, 1. So it's the same information just presented in a different way. And like I said, the histogram makes the shape more obvious. So we can see here that we have a shape where the histogram goes up, down, up, and then down again. Here's another example of a set of data where 20 people are telling us their heights. We get this table right here. This is the table of our answers. And then if we make this into a histogram, we get this type of shape right here. This type of shape would be called a normal distribution, or a bell-shaped curve. And it's not perfectly normal, but I just did the best I could to make a histogram that looks pretty close to a normal distribution. Notice how when you have a normal distribution, most people are in the middle. So see how we have 12 people who are between 5 feet and 6 feet tall. So most people are at the middle of height. Most people have medium heights, and we have fewer and fewer shorter people down here, and fewer taller people down here. We have very few people shorter than 4 feet down here, and very few people taller than 7 feet. So this normal distribution is actually a pretty realistic type of shape for height. Height would usually follow this type of shape in real life. And this is just outlining the histogram with this bell-shaped curve. This normal distribution. Like I said, if it peaks at the left end, it's skewed to the right. If it peaks at the left end and trails off to the right, it's skewed to the right. I was trying to think of an example of something that would follow this type of shape. And I was thinking about fast food employees. such as people who work at McDonald's or Burger King. Um, in a fast food company, you have um, a lot of cashiers who make um, a few dollars per hour, maybe I'm not sure what it is now, maybe $8 per hour or $7 per hour. So let's think about the incomes of fast food employees. In a fast food company, you have a lot of cashiers who have lower incomes. The cashiers probably have the lowest incomes of all people at the company. So they're at the low end down here because they're at the left end because they have the lowest incomes, and they have the tallest bar because there's a lot of them. Further toward the right, we have maybe the assistant managers who make more money than the cashiers, or maybe a little bit more money. Since they make more money, they're further to the right than the cashiers are. But since there's fewer assistant managers than cashiers, so that's why their bar is shorter. And if we go further to the right, we maybe have managers who make more money, but there's fewer of them than the assistant managers, so their bar is shorter. And then I'm not sure what these people would be. Maybe a higher level manager who makes more money, but there's even fewer of them. And then up here we have, it looks like one person because this bar goes up to 1. This would probably be the CEO of the company, and this person makes the most money, so they're furthest to the right. But there's only one CEO, so the bar is very short. So the incomes of fast food employees probably follows this type of shape. And my first job was working at Burger King, so I was actually one of these people down here in this bar down here. I was one of the cashiers who makes the lowest amount of money. That was my first job when I was in high school. And you can see the shape which is skewed to the right. So whenever something is skewed to the right, you have a lot of people with lower numbers and fewer people with larger numbers. In my example, it was talking about how in a fast food company, you have a lot of people with lower incomes down here, such as cashiers and assistant managers, and you have fewer people up here who make more money. So what about something that would be skewed to the left? The example I was thinking about was maybe people who work at a hospital. I'm not totally sure if that would be correct, but I'm just thinking that that could be skewed to the left because let's think about the incomes of people who work in a hospital. You have a lot of doctors and physicians and who make a lot of money. So those doctors and physicians are down at the right end because they make a lot of money. They have higher incomes. And there's a lot of them in the hospital, so they have a tall bar. And then when we move down here toward the lower incomes on the number line, we might have nurses who might make a little bit less money. And then down here, we might have the support staff of the hospital, such as receptionists or maintenance workers who make less money. So they're down toward the left end of the income number line. And I'm thinking that there might be fewer of those maintenance workers compared to the doctors over here, so their bars would be shorter. So it could be that the incomes of hospital workers follow this type of shape. Here's another example that's commonly used for skew to the left and skew to the right. If a classroom full of students takes a difficult test, you have, um, if you make a histogram of the exam scores, then you have a lot of people who are getting lower scores down here because a lot of people did poorly. You maybe have a lot of people with D's and F's down here, which is why the bar is so tall. And then fewer and fewer people are getting these higher grades up here. So you have fewer C's, fewer B's, and even fewer A's if the test is difficult. If the test is easy, then students' grades will follow the other shape, which is skewed to the left. If the test is easy, then a lot of the students in the class will get the high grades down here. I mean, a lot of the students will get A's, which is why this bar at the right end is so tall. Actually, this is B's, but a B is still a pretty good grade. So we have a lot of students getting B's right here. We have fewer C's, fewer D's, and even fewer F's. Very few people are failing down here. So if the test is easy, then the students' grades will be skewed to the left. This is just talking about the mean, median, and mode of the data. We'll talk about this right here. Well, if the column of data is skewed to the left, the mean will be a larger number than the median, meaning the mean will be to the right of the median. If the data is skewed to the left, like this, then the mean will be a lower number than the median, meaning the mean will be on the left side of the median. So you can just think of it as the mean being pulled in the direction of the skewness. If it's skewed to the right, the mean is pulled toward the right end, and then the mean is to the right of the median. If the data is skewed to the left, then the mean is pulled toward the left end, and the mean is on the left side of the median. I think that's a good way to remember it. If the column of data follows a normal distribution, then the mean and median are both the same number. Actually, if the data follows a normal distribution, the mean, median, and mode are all the same number. We talked about kurtosis, which involves the amount of peakness in the histogram. If the histogram has a shorter and wider peak than a normal distribution, meaning if the shape is flatter than a normal distribution, then that column of data has a negative kurtosis. If the column of data has a taller and narrower peak than a normal distribution, then that column of data has a positive kurtosis. Here's, I think this is a good picture right here. I got this from a website. This blue line is a negative kurtosis. This red line right here is a normal distribution, and this green line here is a positive kurtosis.